Imagine your plant is running normally. Motors are on, PLC panels are healthy, and VFDs are controlling the process smoothly. But suddenly, the light blinks for just a fraction of a second, no complete power failure, no breaker trip, just one small voltage dip. But immediately, when VFD trips, a contactor drops out, the PLC shows fault, and the production line stops. Now, the question is, if power was not completely gone, why did the machine stop? This is where the voltage sag and voltage interruption becomes important. In many industrial plants, the real problem is not always a blackout. Sometimes a voltage dip lasting only few cycles is enough to disturb the sensitive equipment and stop an entire process. So in this video, we'll understand what voltage sag and interruption are, why they happen, how they affect electrical systems, and what practical solution can reduce their impact. Now, since this video is part of our power quality series, you can also check the full playlist from the link in the description. Let us start with the voltage sag. A voltage sag is a short duration reduction in RMS voltage below the normal operating level, typically between 10% to 90% of the rated voltage for durations from 0.5 cycles to 1 minute. In simple words, voltage sag means the voltage has dropped from for a short time, but it has not become zero. For example, suppose your system voltage is 415 volts. During a disturbance, the voltage suddenly drops to 280 volts or 250 volts for a few cycles and then comes back to normal. That event is called a voltage sag. The important point here is duration. Voltage sag is usually very short. It may last from around half a cycle to few cycles, or sometimes up to a few seconds depending on the system condition and protection operation, but typically less than a minute. In power quality studies, voltage sags are commonly associated with short duration RMS voltage reduction caused by system faults starting from maybe large motors, transformer, or sudden heavy loading and things like that. Now, do not get confused between the voltage sag and under voltage. Under voltage is usually a longer duration condition, typically more than a minute. For example, if a supply voltage remains low for several minutes due to poor voltage regulation or overloaded feeders, that is under voltage. That is not voltage sag. But voltage sag is a sudden dip and a recovery. It comes quickly and it goes quickly. But in that short time, it can create big problems. Now, let us understand what is voltage interruption. Voltage interruption means the supply voltage is lost completely or almost completely for less than 1 minute. In voltage sag, voltage reduces but still remains available. But in interruption, voltage becomes zero or nearly zero for less than a minute. Again, please pay attention to the duration here. For example, if the supply to a feeder is lost because a breaker opens, then the connected load sees an interruption. If the supply comes back after a few seconds due to auto reclosing, it is called a momentary interruption. If the supply remains off for a longer time, typically more than 1 minute, it becomes a sustained interruption. There is a difference between these two. A momentary interruption can happen when a utility system clears a temporary fault. For example, a tree branch touches an overhead line, create a fault, and the protection system trip the feeder. After a short delay, the reclosure closes again. If the fault is cleared, supply is restored. From the customer side, this may appear as a short power cut of 1 or 2 seconds maybe. For home user, this may just look like a blink of the light, that's all. But for an industry user, this may stop an entire process. Now, the next question is, why do voltage sags and interruption happens? Well, the most common cause is fault on the power system. A fault means an abnormal current path. It may be a single line to ground fault, line to line fault, double line to ground fault, or three-phase fault. And if you want to learn about what are the different types of fault, what is their severity in power system, I do have a dedicated video on that. You'll get link for it down in the description. You can definitely check that out after this video. In practical distribution system, single line to ground faults are very common, especially on overhead lines. When a fault occurs, very high current flows. Because of this high current, voltage drops in different parts of the network. The protection system detects the fault and trips the breaker or reclosure to isolate the faulty sections from the other system. Now, during the time between fault occurrence and breaker operation, the voltage at nearby load drops. This is experienced as voltage sag. If the fault is on the same feeder supplying your plant, then you may first experience voltage sag during the fault and then interruption when the breaker opens. And that's why voltage sag and interruption can happen one after another. If the fault is temporary and the reclosure successfully closes again, the interruption may last only few seconds. But if the fault is permanent, the breaker will trip again and the supply may remain uninterrupted until the supply will remain interrupted until the fault is located and repaired. And now this becomes a sustained interruption. Now here is an important point. A voltage sag can happen even when the fault is not on your own feeder. Suppose your plant is connected to feeder number 1 from a substation. A fault happens on the feeder number 4 from the same substation. Your feeder is healthy, but during the fault, the substation bus voltage may dip. So your plant will also see a voltage sag. In this case, your supply may not get interrupted because your feeder breaker has not tripped, but your equipment may still trip because of the voltage sag. This is why many site engineers get confused. They say our feeder did not trip. Then why did our VFD trip? And then the equipment manufacturer is blamed for that. But in reality, it may not be the manufacturer's fault, but it's the voltage sag due to the fault somewhere else in the system. The fault may be on a parallel feeder. It may be on the transmission system. It may be on the distribution network. It may be even inside the nearby large consumer's plant. And to be very honest, the equipment that you have connected in your system, it does not care where the fault happened. It only reacts to the voltage that reaches its terminal. If there is problem in there, it will trip. Another common cause of voltage sag is starting of large motors. When an induction motor starts, it draws high inrush current. This starting current can be 5 to 7 times the full load current, depending on the motor and starting conditions, of course. If the supply system is weak or if the motor is very large compared to the transformer and the feeder's capacity, this high starting current can cause a temporary voltage dip. And if that sag is deep enough, some sensitive devices will trip. And this is why proper motor starting study is important. Soft starters, VFDs, star delta starters, auto transformer starters, and correct transformer sizing are not just for reducing mechanical stress. They are also to help reduce voltage sag during starting. Another cause is transformer energization. When a transformer is energized, it can draw magnetizing inrush current. This current can be very high for a short duration. In some cases, especially in weak system, it can cause voltage dip. Similarly, sudden switching of large loads, capacitor bank switching issues, short circuit in downstream equipment, welding loads, arc furnaces, and heavy fluctuating loads can also contribute to voltage variations. Now let us talk about the impact of voltage sag and interruption. In earlier days, many industrial loads were mostly electromechanical. Motors, heaters, lamps, and simple contactor-based circuits could tolerate short disturbances to some extent. But modern industrial plants are different. Today we use PLCs, we use VFDs, servo drives are there, control relays are there, electronic power supplies, sensors, communication models, SCADA system, and automated machines. Now these devices are very useful, but many of them are also very sensitive to voltage dips. A very short sag may not stop the normal motor immediately because the motor has inertia. But the control circuit feeding that motor may trip. The contactor coil may drop out. The VFD may detect under voltage. The PLC power supply may reset. The relay may operate. And once the control system trips, of course the process will stop. This is the main problem. The main motor may be capable of riding through that disturbance, but the control system may not. And such kind of disturbances happen in the industry, especially if the industry is process industry. The impact can even be bigger. The line may be stopped for several minutes to several hours, and that directly cost you money. The cost of voltage sag is not only the cost of electricity loss. In fact, electricity loss may be the smallest part of it. The real cost comes from production downtime, material wastage, machine resetting, manpower loss, quality rejection, delayed delivery, and sometimes equipment damage as well. So this is why power quality is not only an electrical engineering topic, it is also business continuity topic. So those are the impact, those are the causes. But what are the solution to this? Let's talk about the solutions for this issue one by one. Before we go deeper into the solution, here is one small request. If you're finding this explanation useful, consider subscribing to the channel. On this channel, I try to simplify electrical engineering topics like power system, power quality, substation, switchgears, and many more. Right? So thank you so much for that in advance. Now let us continue. To understand voltage sag properly, you need to look at two important characteristics: magnitude and duration. Magnitude means how deep the voltage sag is. Duration means how long the sag lasts. For example, a voltage sag to 80% of nominal voltage for 5 cycles or 100 milliseconds for 50 Hz frequency may not affect some equipment. But a sag to 40% for the same duration may trip many devices. Similarly, a sag to 70% of for half a cycle may be tolerated, but a sag of 70% for 1 second may cause equipment to shut down. This is why equipment sensitivity is usually studied using voltage ride-through curves. A voltage ride-through curves tells us how much voltage drop an equipment can tolerate and for how long. Some equipment is sensitive mainly to voltage magnitude. For example, undervoltage relays or some contactors may trip when voltage fall below a certain level. Some equipment is sensitive to both magnitude and duration. Electronic power supplies, PLCs, and drives often behaves like that. They may tolerate a very short dip, but if the dip lasts longer, their internal DC voltage fails and they trip. This is why two pieces of equipment may behave differently during the same voltage sag. One VFD may ride through, another VFD may trip. One contactor may hold, another may drop. One PLC may continue, other may reset. So when engineer investigate voltage sag problem, they should not only ask what was the supply voltage, they should also ask what was the minimum voltage, how long did it last, which phases were affected, which equipment tripped, what is the ride-through capability of that equipment. So there is no single solution that works for every site. The correct solution depends on the process, equipment sensitivity, cost of downtime, fault history, utility system, and budget. But in general, the best strategy is to solve the problem as close to the sensitive load as possible. Why? Because protecting a small control circuit is much cheaper than protecting the entire plant. For example, if 200 kilowatt machine trips because of 230 volt PLC power supply resets, you may not need a UPS for the full 200 kilowatt machine. You may only need backup for ride-through support for the PLC control relay. This is very important practical point. Many engineers immediately think about a large UPS system or big power conditioners. But first, identify what is actually tripping. Is it the main motor? Is it the control circuit? Is it the VFD? Is it the contactor coil? Is it the protection relay? Is it the PLC power supply? Once you identify the weak point, the solution becomes more economical. The first solution is, of course, better equipment specification. When buying critical equipment, check its voltage sag ride-through capability. Ask the manufacturer how much voltage dip the equipment can tolerate and for how long. For critical industrial equipment, it is better to specify that the equipment should ride through common voltage sag conditions. Some industries follow standards and guidelines that define ride through expectations for sensitive equipment. This is the cheapest stage to solve the issue because you are preventing the problem before installation. The second solution is control power protection. Many shutdown happens because the control power is not stable. So, providing a small UPS, DC power supply backup, capacitor based ride through module, or control transformer support can help. This can prevent unnecessary tripping during short interruption. But UPS selection should be done carefully. For small control loads, this is often one of the most practical solutions. The third solution is using voltage sag compensator or dynamic voltage restores. These devices detect voltage sag and inject missing voltage so that the load side voltage remains within an acceptable range. For example, if the supply voltage dropped to 40%, the compensator injects the required voltage to maintain the load voltage. Some devices operate very fast within a fraction of a cycle. These are useful for sensitive industrial loads where downtime cost is very high. The fourth solution is UPS for larger load. An online UPS continuously supplies the load through the rectifier and inverter. It provides strong protection against sags and interruption, but it has losses, cost, battery maintenance, and space requirement. A standby UPS normally supplies load from the main line and transferred to the inverter during disturbances. It is cheaper, but transfer times become important. If the load cannot tolerate even few milliseconds, standby UPS may not be good enough. A hybrid UPS combines features to provide better regulation and a ride through. UPS systems are excellent for IT loads, control system, instrumentation, and selected critical machines. But using UPS for very large industrial loads can become expensive. The fifth solution is a motor generator sets or flywheel system. A motor generator sets uses mechanical inertia to ride through the short interruptions. The motor drives a generator and the generator feeds the load. When input power dips or fails, the rotating inertia continues supplying power for a short time. Flywheel energy storage works on the similar basic idea, but with modern high-speed flywheels and power electronics, this system can provide ride-through for short interruption without depending only on batteries. They are useful where frequent short disturbances occur and high reliability is required. The sixth solution is a static transfer switch or fast transfer switch. If a facility has two independent power sources, a transfer switch can shift the load from one source to another when a disturbance is detected. A conventional transfer may take more time. A fast transfer switch can transfer in few cycles. A static transfer switch is using power electronic can transfer even faster. But there is one important condition. The two supplies must be truly independent. If both supplies come from the same substation bus, then a fault affecting the bus may cause sag on both sources. In that case, a transfer switch may not solve the problem. So before applying these solutions, the source arrangement must be studied properly. And certainly the utility can also do improvement to avoid voltage sag. Utilities can reduce sag and interruption frequency by improving protection coordination, using fast fault clearing, maintaining overhead lines, trimming trees, installing animal guards, improving insulation, using underground cable where it's justified, adding feeder automation, and improving system design. But from customer side, utility side improvement is not always fully controllable. That is why industrial plants usually combine utility coordination with internal protections for critical loads. All right, so now let's summarize the concepts clearly. Voltage sag is a short duration drop in RMS voltage less than 1 minute. Voltage interruption is complete or near complete loss of voltage for less than 1 minute. The most common causes is the fault on the power system. The fault may be on your feeder, a parallel feeder, or even the transmission system. Other causes includes large motor starting, transformer energization, sudden heavy loading, and switching events. The impact is high because modern industries use sensitive electronic control. Even a sag lasting only a few cycles can trip VFDs, PLCs, and other control equipments. The practical solutions we discussed includes better equipment right through specifications, control power UPS, voltage sag compensators, online or standby UPS, motor generator sets, flywheel system, static transfer switch, and then of course the utility side improvements. But the most important engineering lesson is this. Do not treat every voltage sag problem as a full plant power failure problem. First, identify what is tripping, then protect the most sensitive and most critical part. That is how you get the best technical and economical solution. In the next video, we'll discuss about the transient overvoltage in the same way we discussed the voltage sag and interruption. And if you do not want to miss out on that update, consider subscribing to the channel. Or if the video is already available, I'll put that down in the description. If this video helped you, then do like this video and do share it with the people who do you think will be benefited by knowing all this. If this was helpful, then do comment your thoughts about this video. Thank you so much for watching, guys. I'll see you in the next one. But till then, keep watching, keep learning.